Hello everyone, I'm Niloofar Saeedzadeh Khaanghah, PhD student from the Free University of Bozen-Bolzano. Welcome to my presentation, which is about thin film thermistor temperature sensors on animal-based substrate. Thin film electronic technology has opened the door to create innovative electronic devices, which is really a significant shift from heavy and bulky devices to those ones which can offer remarkable advantages like large area fabrication, flexibility, lightweight design, conformability, stretchability, unobtrusiveness, also the possibility of having transparent, biodegradable, and transient electronic devices. Temperature sensing is one of the important fields where thin film electronic comes into play, because nearly in all domains we need to have temperature sensors that can monitor accurately the temperature. Like healthcare monitoring, food industry, fire and safety, environmental and agricultural monitoring, energy management, and automotive sector. Though we have already devices that thin film electronic may enable us to have highly sensitive and flexible temperature sensors, we still have this growing concern regarding the electronic waste. And as one of the most important part of this electronic waste comes from the substrate, there is a growing demand regarding to have natural and biodegradable materials to be used as electronic substrate. Therefore, we see that recently there have been some researchers that used natural materials like wood, paper, leaf, and stone-based materials as electronic substrates that are promising materials that not only can break down into harmless components, but also provide nice-looking substrates for electronics devices. Therefore, here, my research is extended to using animal-based substrate, which is inspired by Asian people civilization resourcefulness, by using naturally available materials around to meet their needs. So I have buffalo horn and mother of pearl here, which we bought them from commercial supplies, and we explored that these materials are normally wasted as byproducts in food, agriculture, and fishing industry, therefore addressing the desire to use natural materials in electronic substrate. The surface of the buffalo horn was polished by the manufacturer. As you see, the AFM measurement showing the surface roughness here with maximum vertical roughness of 0.12 micrometer and a root mean square of 9 nanometer. However, the mother of pearl has a smoother surface with some horizontal waviness that the confocal microscope showed a maximum height of 22 micrometer. So what I did was I used this substrate to fabricate thermistors on top. And this is the process. We took this substrate one by one in the sputtering tool. To pattern the substrate with the metal contacts, I used a shadow mask and deposited zinc on top. But as we know, thermistor has another layer of semiconductor layer. So we used a second layer of shadow mask and deposited indium gallium zinc oxide to connect the metal contacts together. This should be the pattern of a thermistor with two stack layers of material. And here are the fabricated thermistors on my substrate. So I started characterization by taking a current voltage characteristic first to check the conductivity. As you see, there is a nice ohmic contact and with an average resistance in order of kilo ohm. And as we use different sensor patterns with different W barrel ratio, you see the difference between resistance. To do testing the sensing performance, as we know, one of the common way is putting the sensor on top of a hot plate and then using a microcontroller, then doing the cycling. But here I use a different heating methodology. As you see in the picture, I use a heater which is silver printed serpentine pattern on a capstone layer. And I applied this heater right on top of the sensor. And what we did was we applied voltage to this heater and received heating in return. And I used also a kind of now commercial PT100 sensor to monitor the difference between the temperature. Also, this setup had a LabVIEW program and a digital multimeter to monitor the signal. Here you see the plot of normalized resistance versus temperature, which shows a significant hysteresis, as you see to the plot. As we start heating and cooling, there is a steep slope showing that the sensor is highly sensitive to the heating and cooling. However, as soon as the heat dissipates into the substrate, the sensitivity goes down. So by taking the linear behavior between 30 to 70 degrees, the sensitivity for heating process is 0.22% to degree and 0.16 for the mother of pearls. And this large hysteresis is comparable to other thick and voluminous substrate, and is normally attributed to the heat capacitance of the substrate that retain and release heat gradually. Here you see the reliability test of the sensors, showing that our sensors have quite reliable signals over multiple cycles with mean orders. And finally, we did also the dissolution test. We already have papers showing that IGZO semiconductor is dissolvable. However, what they did was they used a kind of dissolvable substrate and had IGZO on top. And when they did the dissolution test, it was not clear either it is the substrate or the semiconductor dissolving. But here we aimed to show this, that IGZO is dissolvable or not. And what we did was we used a tiny container and applied right on top of the sensor that we wanted to monitor the behavior. And we added 800 microliter of deionized water on top. And after nearly 1 hour stabilization time, we saw that it took 35 hours to reach the open circuit. As we know and had the experience from before, that zinc dissolution rate is so fast, nearly 1 hour or a couple of hours based on the material thickness. So monitoring this long time of 35 hours of dissolution really shows that it's first the semiconductor layer that dissolved and then the zinc layer that took this long, comparing to the dissolution rate of the zinc. So this is the thermistor that we have two stack layer. First, it was the zinc that dissolved. In conclusion, for the first time, we used animal-based substrate to fabricate thermistor on top. And what we did was depositing 2 layers of materials, zinc and indium gallium zinc oxide semiconductor on top, and fabricated the thermistors. We did the characterization, as you see. So sensors showed quite stable and reliable signals during multiple tests and high hysteresis. Also, the solution test was successful on these sensors. Thank you for your attention.